Okay, we will continue our talk on ship motions in irregular waves. See, we just spoke about this transformation, no? That is, how do I get encounter spectrum now? The procedure is straightforward, excuse me, simple, because what we have to do, see, earlier we had on that for a 0 speed h omega against omega, and I obtain this response, say I call it, but now I have to do the same thing here. I obviously have to write this h omega e, which will also look something like that, and I multiply the corresponding a with corresponding b square, I end up getting procedure is very straightforward. See, earlier I went this way for 0 speed case when there was no speed, because this remains same as I viewed, and obviously response also is function of omega, because you would have calculated the responses assuming that there is no motion. Here earlier I went this way, now I have to just go this way. So, the procedure remains as simple, just that I have added one line here to here, and this I have seen that there is a formula, right. That formula is very simple, that you know, omega to omega e, if I were to draw one table, then there is a first line omega, next line omega e, third line is s omega, fourth line s omega e. So, it is very straightforward, you do that and end up getting this. So therefore, what we find out is that this procedure is very simple. Okay, this is what we call response spectrum. Then what? So, I will now now I know the procedure, how to get from here to there. Now, we will talk about this little bit. Okay. See, if you tell a shipyard or somewhere, well, the response of the ship, you show him a plot, okay, with some kind of numbers here. Nobody is going to be impressed. Nobody likes it. They want a number. They will tell you, okay, tell me how much it is rolling or heaving. So, you have to crystallize that or quantify that in some number. Okay. Now, remember, that is why I will discuss this and how do we really represent that. So, let us look back at the response spectrum. So, again I am calling it heave, so but it can be any response, which we will come to in a minute. Okay. Let us take this forward speed case only. So, this is my response spectrum we call. But before that, let me tell one small thing that I keep missing. See, I call this h omega, right? And what did I say? I say that s, well, let me look at this one, z omega e, h omega e square into s omega e. This is what we have been saying, right? See, this term h omega e square, okay, this h omega e square, look at that. In our subject, this is called as RAO, response amplitude operator. So, you see, I will just write down this. So that see, the procedure is like that, no? The response spectrum is RAO square into wave spectrum. Actually, here I want to tell you one thing, you know, before coming to this part, let's keep it aside. Some people call this square, that is, this square itself as RAO. So, there is some kind of an ambiguity in some time. See, technically I would prefer personally transfer function to be a better word, because in other literature, other subjects, they use the word transfer function. But historically in marine literature it has come to known as RAO. Okay. So, we need to know this, everybody will say RAO.
So, the response function by the amplitude?
Yeah, this part. Now, here actually some people, some book refer square of that as RAO, that means what square of this as RAO, so that response spectrum become RAO into wave spectrum, whereas some other book will call this as RAO itself, so that response spectrum is RAO square into wave spectrum. So, the definition of RAO, there is some ambiguity, means what I call RAO by person X, another person may call square of that as RAO. We are going to call here this as RAO, not the square, because this well, this is a better in my personal opinion, because it is a transfer function output by input, no square, no cube, no operation involved. And why the word also is meaningful, no, RAO, because you are operating this on the wave spectrum to get response spectrum. This is from there here the word has come. See, you operate on the wave spectrum this operator, square of this operator, to get response spectrum. So, we call RAO. What is RAO therefore? Well, RAO is nothing but this graph. Go back, what is RAO? It is nothing but response in regular waves. RAO is just a term. So, when I say find RAO, which means I am telling you find out how the body behaves in regular waves. This graph or this graph, RAO or transfer function, is a representation of regular wave response in regular waves. Or supposing I did find out a ship's behavior, how much it behaves in say 50 meter long wave, 100 meter long wave, 200 meter long wave, over a range of lengths, I will plot them against some parameter here which can be length or omega, and this side output per unit amplitude, that is RAO. Okay. So, RAO is always that, I mean we are calling it. Now, having said that, I should have, because see, as you know, in every subject there are certain typical term. I mean I have said that we use the word resistance, whereas most of the people use drag in mechanical engineering or in airspace. Aircraft, you will not hear the word aircraft resistance, or you will hear a missile resistance, you will hear missile drag. Okay. But we call ship resistance. So, it is a question of like nomenclature. So, similarly we use RAO. You go to electrical engineering, everybody use transfer function. Any experiment you do, you have an output by input voltage. You call transfer function, or you call the calibration constant, or whatever. But we call it here RAO. So, let us keep in mind that. Now, you see now this. Now, if I see what has happened, it turns out if I were to assume that to be again a narrow band, and this is what people say, that the RAO which see this is narrow band Rayleigh spectrum, we said, you are multiplying with that. So, what would happen multiplying with that, getting that, the presumption is that it does not change too much the shape as far as statistical quantities go. So, it is presumed that this also is fairly good represented by a narrow band Rayleigh spectrum, although you have seen that if I see this following wave, things look very different. Okay. But that will come to that again. So, if I have this, then what happen? Let me look at this area under that. So, so let me call this Mn as n. What? Yeah, absolutely, yeah, H, is very true. I am sorry, this Z A omega by, right. Actually, H omega is RAO for us. That's right, absolutely true. Thank you. Yes, it's not H. Yeah, this what I mean, that output by input, that part which of course is which is what I call H omega, is basically RAO for in our case. So, now see, okay, with that clarification, let us look back at that. let us take an nth moment of this graph. This will look like that. Mn is omega e power of n sz omega e d omega e. Now, it turns out that since it is a narrowband spectrum, all properties of statistical importance again are connected to these various m's. M0, well, M0 is going to be area, and in fact, most people are here interested in absolute value, amplitude, not in the time period, how much it is rolling, etc., etc. So, what is happening that now formula theories will tell me that average value say z, in this case response is z, z RMS. These are formulas available. Like that. See, what I am saying, therefore telling is that what happen is you can find out formula for all quantities of interest in terms of area. So, remember that h 1/3 was 4 root m0. Of course, it was 4 because it was height, amplitude would have been 2 root m, same formula. All the ratios are same as was in wave. Not only that, because it is a narrowband spectrum, you can also find out what is the probability of z exceeding, for example, z star. What is the probability of z remaining within this bound? What is the highest wave z you would encounter in 100 cycles or 1000 cycles? What is the chance of h becoming more than 0.1%? I mean, any quantity of interest is available because same formulas will apply. Obviously, people do not go for all of them. Mostly what happened, we will tell this, supposing it was roll motion. Now, look at this area also, okay, we will come to that. But normally when you want to quantify, you will quantify that, or in some case of some responses you will quantify in terms of occurrence. See, for example, there are response like slamming, we will come to that afterwards. One would like to know in 1 hour how many times certain value will exceed some value. For example, let us say seasickness, it turns out that if your acceleration is some value with a certain period, you tend to vomit. Then we will define some parameter, and then we will say what is the chance of this parameters occurring. You can find out from the spectrum. So, all this becomes possible. So, it becomes really useful. Only one thing that I need to say, because sometimes the spectrum do not look like a narrowband Rayleigh. So, there is sometimes a correction factor is introduced, like you multiply all of this you can multiply with a correction factor. You can multiply all of them with a correction factor, and this correction factor is just introduced sometime in order to like account for the fact that the response spectrum sometimes is not so closely as narrowband Rayleigh spectrum. So, this is given something like 1 minus epsilon, theoretically already given, where epsilon square you will find out that frankly if you will find out that if the spectrum was absolutely narrow like that, then this term turn out to be basically 0 and correction will be 1, because m0, m4 and m2 square will become same. You will find out, I am leaving it to you. If it will stick like that, m4 is going to be omega 4 into this value m0 is, so this will become 0. No, m0 m4 minus m2 square by m0. What I am trying to say that this is some kind of a correction factor introduced for the fact that the spectrum that you have may not be necessarily narrow band, And what I was trying to tell you is that if you take a theoretically a completely narrowband spectrum, which means a stick, something like that, you will find out that this quantity becomes equal to 0, means CF is equal to 1, which tells you that strictly absolutely a narrowband spectrum, there is no correction. The further it goes from that, there is some correction. Sometimes people use, sometimes people do not use. The value of them will lie between 0.9, 0.8, 5, etc., typically for a spectrum. Sometimes you may want to use it, that is all. So, with that you can get this number. So, what is happening? You are getting all this number that you want in terms of area. Okay. See, now I want to look at some of this units, just so that we do not have any confusion on the units. See here, this side is what? This side, let us look at this again. Now let me call this a response, any response. Let me now generalize it. Instead of Z, let me call it R representing any response. So, that is going to be RAO for the response of that response square into S omega E, or I am going to call this as response amplitude by wave amplitude square into S omega E. Okay. So, this we know. This here R A is amplitude of the response, and this is omega E. I am just generalizing it. Now, let us say when this is heave, what is the unit? It is meter. Meter by meter square gives you meter square. What is the unit of this? Meter square second. What is the unit of this? Meter square second. What is the unit of the area? Meter square. So, square root that meter. Take roll degree. What is the unit of this? Degree square by meter square. So, degree square by meter, say here degree square by meter square into meter square second gives you degree square into second, multiplied by 1 by second give you degree square. So, you get degree. So, what is happening? You see, you will find out here this meter square second will leave unit of the response square into second, and 1 by second give you square of the unit. Why I am saying this? Because people are confused. I could have this RA as pressure at a point. What is the unit of pressure? Kilonewton per meter square. You do that, you will find out the unit is going to be here kilonewton by meter square, square of that into meter square second. If you do that, the whatever unit comes out. So, there is no ambiguity with respect to units. There is, okay. So, this procedure of breaking it down applies to any response which behaves linearly with waves. Important thing is that it must be H omega must be equal to R omega by A. This must be true, which what does it mean? It means that response is linear with respect to A, because RA by omega is constant for a given omega. When I say R by A is constant for a given omega, I am saying basically that response, that R is a linear function of A for that omega. So, whichever responses depends linearly on A, this procedure remains valid, and there is no ambiguity on that. Okay. And this procedure, we will work out some of the problems at the later part of that or something like that, but let me look at an interesting part of RAO of acceleration. Sometime you want to find out acceleration here. You do not want to find out the motion, but acceleration. Physically important, because suppose there is a gun mount here, the load is going to be mass into acceleration. So, you are interested in acceleration. So, now how do I find RAO for acceleration? My Z, let us say heave case was ZA into how much is Z dot velocity? Well, let us say with a minus sign will come. This is okay. How much is Z dot dot? So, what is now RAO? I am writing this as RAO for Z is amplitude by A. Okay. What is my RAO for Z dot? How much is the amplitude of that is omega Z A, right. So, it is omega Z A by A. Well, of course, we should probably put omega E here. Agree? What is RAO for Z double dot? It is going to be omega E square, and of course, actually let me write two step. It is omega E RAO So, you see the RAO for velocity is omega times RAO of displacement. RAO of acceleration is omega times RAO of velocity is equal to omega square RAO of displacement. Now, see how I can get from one to other spectrum. So, I have this spectrum here SZ omega E. Now, I want to find out velocity spectrum. How much I am going to have that? See, remember this value is what? This value SZ omega E is essentially RAO of Z square into S omega E. Now, this value SZ dot omega E is supposed to be RAO Z dot square into S omega E, that is equal to omega E square RAO Z square into S omega E. This is equal to SZ omega E. So, in other words, all I have to do is to multiply this omega E square to get the value. Okay. See, this is interesting. Therefore, velocity spectrum is obtained from this simply by taking each ordinate into omega E square corresponding value. Now, if you see this acceleration spectrum similarly, exactly, is going to be this into velocity spectrum equal to this into acceleration spectrum. Now, you see you end up getting this, right. Now, look at the area. If you look at the area under that, remember that omega E square Z A omega E, area under that is actually M2 for the velocity displacement spectrum. So, M2 of displacement spectrum is same as M0 of velocity spectrum. Okay, we will come to that. Now we understood this, right, this part, that is let me here put it down in a this way, S Z dot dot omega E is equal to omega E square S Z dot omega E equal to omega E4, okay. And similarly, well, let it be like that. Now, M0, let me call it Z, that is M0 Z means area under the velocity spectrum. Oh, this we know, of course, this is equal to integration of S Z omega E. Now, M0 Z dot area under the velocity spectrum, no, this is Z dot, that is why, is equal to, absolutely, it is M2 of Z. Now, that he wanted to know this thing. So, this is omega E square Z A, this you agree, because this area of this, what is this? This is nothing but M2 of Z. Similarly, you will find that M0 of Z double dot is equal to M2 of z dot equal to m4 of z. So, what it therefore means is that, see, this other two spectrum are, once I know displacement, I can get velocity, I can get acceleration. In fact, sometime I do not have to plot it, because for correction factor in the same table I am calculating the second moment and the fourth moment. If I want to do that, those columns will give me my velocity and acceleration. We will probably work a problem out, something like, or show it little more detail. So, the question is that displacement to velocity to acceleration, absolutely no problem, just multiply it constant. So, the procedure, this entire spectral procedure is very simple. This is the reason why you should not make mistakes, and it is important. See, I like to tell this, that one should not confuse in any subject importance with easiness. I mean, hydrostatic is extremely important. If you cannot make a ship float, never mind whether what is its resistance, because it is sunk anyhow. But then subject wise GM and all very simple, but very important, you just cannot live without it. So, this is also in a similar way very simple procedurally, absolutely algebra. We will see, in fact, people call this post processing in any software. It is 99% finding out the RAO. Having found RAO, you have to just add a few lines of code to get this, and people do not even call the procedure, they may call it post processing sometime of data, because there is, really speaking, there is no hydrodynamics involved, it is an algebra, take this column, multiply, etc., etc. So, but if you did not do that and at the end tell the person that my like 1/3 or significant role is so and so, then he is not convinced about the motion. So, this is why, like yesterday I was telling about long term statistics, same statistics will come from here. See, each one I know the percentage occurrence, then from there I have the spectrum, from the spectrum I know the percentage occurrence. So, for example, I have spectrum number 1 occurring 20% time, I find that in that my theta's chance of exceeding 5 degrees x percent. So, 0.2 into x percent, whatever into that, like that I get the final probability. That is exactly how I am doing it, or we are doing it. Okay. So, this part is all very well like taken care of. Let us look at some of this way that we can do, for example, problem or like workout. Let us look at this way. See, instead of a problem, supposing what will happen typically you will have regular wave response, that means you will know RAO omega E. Now, this RAO omega E can be given in many forms. Many times you can be given in terms of not omega E, but in terms of another parameter. For example, somebody may say this, that for V equal to so and so, mu equal to so and so, lambda by L versus RAO. In fact, many people like to write in this form. What you have to first do therefore is that transform that to omega E, remember omega E. You can of course do that, because see, lambda, you can get lambda to omega, and then from omega for this V and mu omega E. So, you have to first transform this to this thing to omega E, and you will end up getting omega E versus RAO. Okay. Now, remember one thing, that this omega in RAO is going to be not all the same points. For example, what would happen, let me also draw this spectrum and this thing. So, let me first draw the RAO, then you are going to get RAO a point here, point here, point here, point here, point here, point here, because you are going to do, remember, only a discrete points. You are going to calculate that at some discrete values, not all, obviously, how many, you might be, normally what happen, you would like to calculate this, but as I said, this is the most cumbersome part over a range where the ship responds fairly well. You know, if you take a ship, if you take waves which are very small, you ever go to port and all, you will see small ripples, the ship does not even move up and down at all. So, if the wavelength is much smaller than the ship length, maybe 1/4 or so, no response at all typically. If you go to a very long wave, you will find out that it actually just moves up and down with this, like, you know, simply it goes up and down with the long wave. We have actually done that, goes to 1 for heat motion. Where it responds most, that is, we discussed this part, no, this part, the inertial response and the static response, is where lengths are comparable, wavelengths are comparable to ship length. This you will always see that in your strength calculation you choose, how much do you choose your wavelength, the trochoidal wavelength? You have done strength calculation, right? See, you have done wave bending moment calculation, you assuming a wave profile to be static. No, L by 20 is the height. What was the length you have taken? Why? Why not more length? Why not less length?
Maximum effect happens when
So therefore, the maximum dynamics are involved around. Actually, it is not strictly true though. The truth is that maximum length occurs nowadays found little more than 1, that is about 1.05, 1.06 type, but never by around 1. So you see, L by lambda by L1, which means maybe 0.25 to say 4. This range is what is most important. So you calculate at some discrete values RAO, because each one of them you are spending very long time. I will tell you that you know, like commercial codes for 0 speed like WAMIT that we had, RAO calculation, you know, we paid 25 lakh rupees, okay, for getting a second order. So you can always think back that the cost is proportional to the investment that went in writing a code. The hydrostatic code you can buy for, I give it for 200 rupees or something like that. My point is that it is always proportional, so that tells you the effort that goes in. Okay. So obviously you have only few points. Now the question why I am saying is that this spectrum, of course you have a choice. So what you do, you have that assignment, when you do, you will see you will be having number of points, a given spectrum. You have made this chart number of points against, well, you would have actually first would have no choice. You would have had omega versus S omega, then depending on V this thing you end up getting a particular number. So what I am saying, therefore I have got in one hand table 1 omega versus S omega. This you have done. What you calculate from there, omega E versus S omega E. So you see this value has become this value. This value has become this value, etc. You have no choice on that. This is my graph 1. Graph 2 I have got again, this I said you made it omega E versus RAO. Remember that these values, the one that you chose, these values are not corresponding to these values. So you have to make sure that you do proper interpolation, because what you have to do, you have to choose the, see here if I draw this graph, I have to choose this, I have to choose this value as B, this value as A, to get C equal to AB square. So I require an interpolation in some sense. I cannot simply take, because you see this A equal to B square is for that given omega E. So what happened, I can choose some discrete values here, and at that, for those omega E's I find out what is my this, and at that what is my this. So this operation must be at the same omega E, and typically in any problem, any calculation you do, you are not going to have this. See, for example, this is going to be, let me just give an example, something like 0.5, 0.6, like that it goes. So this will probably become, because I have no control on this transformation, it might have become 0.55, 0.67, like that. Whereas this I would have given at something like 0.4, 0.6, 0.8, like that. So you see, they don't correspond. So you will have to use interpolation, proper interpolation. That is point 1. You will be doing it as part of assignments that I will give it to you. but you need to do that. Okay. That is point number 1. Other thing, this interesting part also we must see. Suppose I have a spectrum. The spectrum is after transformation, let us say 0 speed case only here. Now, I have all the RAO points calculated. What is the point? You have to make sure that my RAO that I calculate covers the existing waves. You see, my C consists of certain wavelengths when I break it down. So, I must find out at least within the wavelength, those wavelengths, the RAO. Beyond that, see, there is no wave here. What is the point of my having the ship responding very badly here? It does not, because what will happen here, my A is 0, B is there, C is going to be 0. This side the same thing happen, B is 0. Similar thing will happen when the response is small. For example, in another case, for example, there is a response going like that and response is like that. Then this side of response 0, I have no point. So, in other words, what is happening? Obviously, typically of course, remember I have no control on this, and when you do yesterday's assignment of spectrum of various H 1/3 and T, you will be knowing what is the typical range of this. You will get a feel, you will understand that they are lying between something like 50 meter to say like 500, 600 meter with a peak around 200 meter long equivalent wave. Now, the main point is I should find out the responses at those range at least. There is no point of finding out response for waves that do not exist. There is no point, they are not matching, because you may say it might respond very badly in a small boat, responds very badly in a 10 meter long wave, but then there are no 10 meter long wave. Okay. And the reverse also is true. So, there is a matching part that is important. When you do a calculation, you must make sure. But this brings us a very interesting point about response of ship, and now I will tell this few minutes briefly on that part. Why it is that not all ships are bad or good necessarily, and why is it that there is a question of tuning there. You see, typically let us take this example. This example is interesting example. Take a spectrum, it is like that. This is at 6 seconds, a peak period 6 seconds. Let us say this is at smaller wavelet, say T Z is 6 seconds, and certain H 1/3 is there. My RAO does not change. Remember, RAO is something like this diagram. It is peaking here. This is my peak response, which is probably equivalent to as far as this is concerned here as 0.5, means 2 pi by 0.5 means about 12 seconds, around that, let us say. See, remember this omega, this is actually, let us say for an offshore structure 0 speed case, let us not complicate things. I just wanted to show you the tuning part, that why is it that it is not necessarily true that all bodies behave badly as the wave becomes bad. What is the correlation? The main point is that the frequencies at which your ship behaves worst should be the kind of waves existing most in the wave, then only it will be very bad. Now, in this particular case, this is my RAO, which does not change of course, because RAO, this particular boat, it has a peak, it has a resonance at 0.5 omega, which means 2 pi by 0.5 gives you about 12 seconds or so, right. At Tz 6 seconds is this peak period for a spectrum. So, if I multiply this 2, I end up getting a response spectrum which is actually a small area, because where the maximum waves occur, my response is small, where the response is highest, my this is small. But now I make this bigger, so I shift it up here. So, what would happen is that I am making this at 8 seconds. Obviously, or rather I can put it, in fact maybe I can put in this graph only. Now, more winds. So, this shift this side. Now, these and these are matching, so I end up getting much larger area. Now, further, but here it is not that bad, maybe larger, but not necessarily that bad. So, what it means is that it is not that necessarily true that as the wave height increases, you will end up getting much worse and worse kind of responses. Okay. Now, I will also want to tell that this is why we talked about this natural period so importantly. You see this natural period, this peak is a natural period, this is the peak at which my response is maximum. Okay. Now, if I have a wave at which my response is maximum, then I am going to have a very bad motion. All right. How much it should be? Now, you see, if you take a barge, very long barge, we discussed this at one time, or rather let me put it this way, pontoon barge and spectrum. This is also interesting about the response part. See, there is a typical spectrum and I will take the 3 different cases. Now, if you take a particular pontoon type of thing, big thing, what would happen? It has got a very high natural period. Small natural period, high natural frequency, because you see T natural in heave is, what is the formula? 2 pi root over of no, omega was m plus a divided by rho g AWP, right. Now, if AWP was very high like a pontoon, my TZ is very low, it can be 4-5 seconds. So, I took a typical wave which looks like that. Typical wave, everyday wave of say C state 4 etc. will have about 10-second period, means omega equal to 2 pi by 10 would give you about maybe 2 pi by 10 gives you how much, 0.6, 0.7 like that, okay, in that region, say 0.6, 0.7 type of somewhere here, or it is basically equal to say 10 second or say 10 to 12 second. But my, remember this low wave, so this will look something like that, go like that, because this natural period is much higher. Okay. Now, this is typical pontoon. Take a typical ship. What is a typical ship? Typical ship has, we have seen that it unfortunately has somewhere here. A typical ship has its natural period about, we have seen that, no, 8, 10, 12 seconds, we have done it earlier. As I was telling you that we have the unfortunate consequence that they are around, not unfortunate, but it so happens that it is around that range if you take any typical values 10, 11, 12 seconds. So, it is somewhere here. Take an offshore structure, you design an offshore structure to make sure that its peak is here. So, it is something like that. Now, multiply this with this, what will you get? Fairly large response, but not that bad, but still quite large response, more or less same as this. You will get response 1 type in this particular wave. This you are going to get much worse, because here this high and this high is more or less close by. This you are going to get practically no response. This is the reason why you design this. Why you design this? Because you cannot, you see here there is a reason. This is a ship, this is a semi submersible. Obviously, from I have mentioned this also earlier, from a operation point of view, a semi submersible which is producing oil is not able to change location. That is point 1. Point 2 is that its operation demands that it has low motion, otherwise if it is heaving then you cannot operate, whereas a ship it may not be so as such. So, therefore, you have to ensure by design that it has very low response, and that is exactly why you of course lower this AWP to make sure TNZ is actually about 20-25 seconds, and if you did yesterday's like calculation, you will find out that around that, even at a very high C state, there are practically no energy. Even if you do high, this side is actually like lower than 20 seconds or so. So, if I have a structured 22 second, 25 second natural period, this peak I am going to have very low response. This is the idea, full idea is that. Okay. Now, so what we find that we have tuning, I call it tuning. A ship would respond badly if its RAO, this part, gets tuned with the wave.
You're saying semi-submersible has lower AWP.
Much lower AWP.
Then time period will be higher.
Absolutely, this is omega, that is the period, no, this is omega. That is what I am saying, time period is 20 seconds or above. So, what I was saying is that if you did those actual values of spectrum formula with h 1/3 even up to 8 meter, you will find out that the spectrum, you will end up getting a shape like that, it is shifting. Even though it shifts, you will find out that even for the highest wave, there is practically no waves beyond above 20 seconds. In fact, only if you do this program and write equivalent T, you will get a physical feel about what are the kind of waves you find in the ocean. We call this, offshore people call this as everyday wave. You know, somebody can say, well, is there no tsunami or long wave? But they are very rare. The wind generated wave given by the spectrum is like that. Now, coming to the ship part, why we can, so what happened? Since I have no getting away of the semi-submersible, I have to design by that, but ship is like that. But how we can manage, the interesting part is this. See, remember, this is my spectrum. Now, this is my encounter spectrum. This is my, very badly it is moving. What I do? I will shift this. How do I shift it? Well, I slow down. We have a slow down, this is going to become encountered. Further shift this side. Remember, so I can detune it. See, I am encountering a wave, say I am at a certain speed, V equal to 15 knots, heading into waves, very high motion. I would think that, well, my natural period is encountering those waves with the same period. Well, I want to detune myself. I want to make sure this and this don't match. Okay, it's few minutes. So, I want to detune myself. How do I do it? Well, I have an option. I can essentially change speed. I can actually change omega e. Now, omega is a function of V and mu, of course, or omega, but we have no choice on that, this too. So, I can change this too. So, typically what I do is basically, see, I cannot increase V because typically I am running at the full V. So, I can decrease V. I can also change mu marginally. I do not change mu typically very hard because, as I keep telling, if I want to go A to B, I do not want to end up going to C by changing my heading. Okay. So, what I do, of course, I make slight change, but primarily I reduce V, and this is what is known as voluntary speed reduction. When I enter a very bad waves, so this choice I have got, the captain has got this choice, so I can get away with it. As it is, I am a mobile. So, if I encounter storm, there is a forecast, there is a storm coming, I can get away from that, I detour from that path. But offshore structure I cannot do, that is the reason why I have this. But what is important, therefore, you find out that, see, encounter spectrum can be shifted. Well, let me, is the last slide I will want to show this. So, two things. Take a spectrum. Now, this spectrum, just absolute spectrum, it shifts with respect to C state. Normally, a low C state spectrum would be on the right hand side with lower energy and the peak height to be at lower, like wavelength. Let us say C state 3 would have maximum energy at 100 meter long waves. C state 6 would have maximum energy for 200 meter long waves. Okay. So, there is a factor with this thing. Now, if I have a particular barge like that, this does not change, but C state shifts to this side. So, you see, in fact, this explains why typically small boats respond very badly in low C state, because low C state, this is at this side and the peaks are maybe 6-7 seconds, and small boats, because AWP is small, etc., also have a smaller typical natural period. So, it is on this side, but if you shift this side, what would happen? Small boats would simply ride the wave. See, suppose you take a small craft, 30-meter long ship, and it is going in a sea state 6 where large waves are 200 meter and above. 200 is about 6 times more length, it will simply ride the wave. But if there is a smaller wave, 50-meter long wave maximum, sea state 2, something like that, it will behave very badly. But take a large ship, big tanker, 300-meter long tanker, it is not going to even feel those 50-meter long ships, but it will become much worse if I have sea state 4, because at that I have mostly 300-meter long waves where it is behaving badly. So, there is this issue of tuning, that is important, and this also tells us why small boats are always bad typically. Of course, you can always see from acceleration, which is omega square into h, there is a square term involved, and obviously you see what happened if this is here, this displacement spectrum, and is shifted further, amplitude acceleration spectrum is omega, each one you are multiplying with omega square. So, if it is farther off, it becomes more area. So, obviously, if I have got larger omega e, then I have more acceleration. Makes sense, no? If 4 seconds to have one oscillation, so I have the entire thing coming in 4 seconds. Another ship, same distance I am traveling in 15 seconds. So, my acceleration is smaller. So, that is why small boats are always uncomfortable, you see, and in next class we will discuss about human comfort level and all. If you are subjecting your body at a very high acceleration, you are uncomfortable, but some level you are comfortable and above. Anyhow, so I am going to stop it at this, and we will continue this discussion little more, and perhaps the problem I was telling we will do next class. But what we understand is the procedure to calculate response in irregular sea is absolutely simple, straightforward algebra, nothing to it. Okay, multiply. So, therefore, you have to make sure you are taking proper. What is important, of course, is studying for that responses eventually. Is it good? Is it bad? Is your ship going to behave properly, etc. And these days it is becoming more and more important. And then going back, you find out the most difficult part in this still remains getting this RAO. This is where efforts go. Those who are not in the subject, practitioners look only the last 1%. Those of us who are inside, we talk about the RAO mostly. Okay. So, with that I am going to close today's lecture. We will get back on this again next class. Thank you.